Hello and welcome to the course on optical communications. In this module, we will begin discussing light sources which are used for optical communications. In the first generation optical networks, which worked around 800 nanometer, not networks, first generation optical links, which operated at 800 nanometer or 0.8 micrometer wavelength of light, the primary fiber type was the multimode fiber and the corresponding light source was a light emitting diode. In second and third generation optical and so on after that first generation ones, we moved away from LED as the optical source or the light source to a single mode optical or more or less a single mode semiconductor laser diode as the optical source, and the fiber was also replaced from a multimode fiber into a single mode fiber. In fact, these two revolutions, if you remember in the first class we talked about the revolutions that caused the optical network, optical networking to just take off, was the first one was the availability of a room temperature laser diode, semiconductor laser diodes, and then with very narrow line widths, that is very important to note, and then you had a single mode fiber whose losses were brought down below the barrier of 20 dB per kilometer. So, you could now couple light from a laser diode which is coming out of the laser diode into a single mode optical fiber, and this was the reason why long distance optical communications was finally able to take off. Earlier first generation optical links were very limited in terms of the propagation distance because you were using multimode fibers, as well as the light source was an LED which was very broad. The line width of a LED is quite large, especially compared to that of the line width of a laser. In addition to this, lasers bring in additional aspects which enable them or which make them very attractive for long distance communications. Chief among them is the coherence that the laser brings with it. Lasers, as opposed to LEDs or as opposed to a tube light, actually have a very high degree of coherence, which means that one can propagate this light over a long distance without it losing its coherence. This is not the module where we discuss coherence, we will leave that discussion to some other module, but it is just important to note that lasers are so much superior compared to the light emitting diodes to enable the long distance communications that they have become the main choice or probably the only choice for light source in long distance optical communications. So, we are going to discuss semiconductor laser diodes, but before that we will discuss laser in general. Okay. So, remember this, our optical fibers today all are single mode optical fibers except for some specialty applications where you are looking for multimode fibers. The sources almost always is a semiconductor laser diode which can be operated in a room temperature and comes with a very small form factor. The LEDs are almost never used as sources for long distance, especially long distance high bitrate optical communications. Okay. With that kind of background, we will begin with study of light sources, we will begin with study of lasers, and we will first look at the concepts that are general to all type of lasers. Okay. Lasers, the idea was started around 1950s, mid 1950s, and then the first laser was demonstrated in the year around 1960, 1962, I am not very sure what exactly is the year, but that was the starting of the 60s, and those early lasers were these huge lasers, the ruby laser or the helium neon lasers, they were all pretty large compared to the carbon dioxide laser, for example. So, these were all pretty large compared to a semiconductor laser, which you can actually see that it would be of this size. Okay. And the advantage of semiconductor laser diode is you can operate this at the room temperature, there is no specific cooling requirement for this laser. You can incorporate a simple cooling technique, not like the running water that is required in some of the high power and different lasers that you would see in a lab. And also these semiconductor lasers can operate with very high degree of coherence, and they can also be part of long distance communication simply because it is very easy to modulate the laser by itself or use the laser light to modulate an external modulator. So, semiconductor lasers have all these advantages, and then we will look into semiconductor lasers, but before that we want to understand what a laser is, what makes up a laser. How is a carbon dioxide laser different from a semiconductor laser? In principle they are essentially the same. The mechanisms by which they laser are maybe or pumped especially are different, but the general principles, if you go to the quantum mechanical principles, they are almost essentially the same. So, we are going to look at general concepts of laser first and then gradually move towards the semiconductor laser diodes in the upcoming modules. So, having said that, let me begin by considering a basic concept that comes up in every laser discussion. Note that we have not yet talked what a laser is, we will talk about that one later. You assume that we have a material. Okay. So, this material has multiple energy levels. Okay. These energy levels are quite spread in terms of the energy. For simplicity, consider this material to have exactly two levels. Okay. These two levels have the energies E1 and E2, with E2 being larger than E1. So, the way we have placed, the one that is closer or the downwards is the lower energy level, the one that is there is the higher energy level. Of course, at these energy levels this material is not empty, it is packed with some atoms. Okay. So, it is packed with some atoms. The number of atoms or the atomic density here in energy level 1 can be written as N1. This would be the concentration or the density in the level 1 having an energy E1. Similarly, you will also have some atoms populated, okay, in the level energy 2. How exactly did these atoms come to energy 2? We will talk about it in a while, but assume that there are some which are found here in the level 2 having an energy E2, and the density of those can be written as N2. Okay. Now, there are three processes that we are going to discuss. Okay. With the help of this simple picture, we are going to discuss three processes. The first process happens when there is a photon incident. Do not ask me how the photon got here, but just take my word that a photon has somehow been incident. Okay. Moreover, the photon has a frequency omega radians per second, such that its energy is given by h bar into omega. So, let me write here because it just you cannot read it here. So, you have h bar omega as the energy of this particular photon. Okay. The difference between the energy levels E2 and E1, let us designate it as delta E. Delta E denotes the difference between the energy levels E2 and E1, and this quantity is obviously a positive quantity because E2 is larger than E1. What happens as this photon enters the material? What happens is that one of these atoms in the ground level can actually absorb this photon and then make a transition to the other level. So, it can go from building on the ground floor to the building on the first floor, if you assume that the ground floor is level 1 and first floor is level 2. So, if you incident a photon, you are kind of pushing the atom to go and make a transition from level 1 to level 2. You are not just interested in having one atom go from level 1 to level 2, you are interested in knowing how many atoms at a time or what is the rate of this transition from level 1 to level 2 that is happening. Okay. This process can be called as absorption process. Okay. It is supposed to be a stimulated absorption, that is there has to be an photon in order to cause atoms to go from lower energy level to higher energy levels. Okay. They go from lower energy level to higher energy level, which means that they have to absorb some energy, and this energy that is being absorbed must be supplied by the photons. Okay. So, you have absorption. The rate of absorption, let us denote this as RABS, and this is by definition the rate at which the atoms in population in level 1 are decreasing. So, there is a minus dN1 by dt, and let us write this absorption. Okay. So, it is clear obviously, right, if the atoms are leaving the energy level N1, then the rate at which N1 is changing will become negative. So, you have a minus dN1 by dt. So, this is the absorption thing. Now, a second process that happens is what is called as the stimulated emission. In the stimulated emission, what happens is that the atom that is there on the top, okay, at the energy level 2 will drop down to energy level 1, okay, under the action of an photon, but the surprising thing is that it will also emit a photon. Okay. So, you get 2 photons for 1 photon incident. Some sort of a small amplification is happening, but we will come to that one later. But what is important is that when atoms go from energy level E2 to energy level E1, they do so by releasing an extra energy in the form of a photon. This photon will also carry an energy of h bar omega. Okay. Now, the difference in the energy is delta E. So, this must actually be equal to the energy of the photon either being absorbed or being created. Okay. Now, you might ask a question, what happens if my input photon actually has a higher energy than the difference delta E? What happens is that this photon will be absorbed, the atom will move from level 1 to level 2, okay. But while moving from level 1 to level 2, it will consume an energy of delta E, but this is the consumed energy delta E. There is a small energy that is still left unused. This energy will be converted into a kinetic energy. So, the atoms will just move slightly to the other distance and then basically settle down after losing all the energy there. Okay. What happens if the energy is actually below the required energy? Then there is very hardly a transition happening. Okay. So, you require the energy to be greater than or equal to or greater than for transition to happen. It does not actually mean that there will not be transition, but that transition is not exactly covered by this particular process which we are talking about. We have to go to the quantum mechanics to look at what is the probability of such a transition happening when the energy is less. Okay. For our discussion in this module and in the next module, we will assume that the energies are exactly matching, so that the incoming photon energy is exactly equal to the energy level difference. And once the photon comes or once the atom comes from level 2 to level 1, the energy will be exactly equal to the energy of the photon h bar omega. Okay. This is absorption process. Now, we have also talked about the stimulated emission process. So, let us call this as stimulated emission, okay, because someone else has stimulated it, right. In this stimulated emission, which we can write this as RSTIM and define it as the rate at which the atoms in second level are decreasing, the density is decreasing in second level, and subscript that with stim. Okay. Finally, you have another phenomenon which is called as spontaneous emission. Okay. With spontaneous emission, what happens is that an atom in N2 can spontaneously go to the level 1. It will also release a photon, because any time when an atom moves from higher energy to the lower energy, it has to do so by emitting the photon in this case. Okay. It does release a photon which will have the same energy h bar omega, but only thing is that this process of going from E2 to E1 without any external input, without any photon being stimulating this process, okay, will result in a photon whose direction will be completely different, random with the and has no relationship with the previously emitted photon or with any other photons that are present there. It will have a random polarization, it will also have a random direction. Okay. So, it is kind of completely random photon that you are going to get, and over if in a material, if these type of transitions dominate the stimulated emission, then you see that on an average there will not be any optical power or optical oscillations, or you will not get any laser action at all. Okay. So, this process which happens without regard of any external input is called as spontaneous emission. So, we can write down what happens with the spontaneous emission, denote it as R spont, which is again by definition the rate of change of density in level 2, but this density is different, this rate of change is different from the stimulated emission. So, this is spontaneous. Okay. Now, Einstein actually showed that, or actually not showed that, actually he postulated that these processes can be described by a couple of constants. In fact, those constants are known as Einstein's A and B constants, and these were this theory was proposed by Einstein before quantum mechanics was properly understood. okay, at least the quantum mechanics of light was not yet understood. We had a fairly good understanding of quantum mechanical properties of matter, but we did not have a quantum mechanical theory for radiation, that is light. Okay. So, this is, that is why it is sometimes called as phenomenological theory, because it kind of is a there is a phenomenon and you are trying to fit a theory into that, okay. Except that this theory was very nice, you know, it gave a very nice match with all the experiments, and this is what we are going to discuss. For our purposes, we do not need quantum mechanics, this is all that we are going to do. What Einstein said was that, look, the way or the rate at which photons are being absorbed from level 1 atoms in order to go to level 2 must really first of all depend on the number of atoms you have in the lower level, right. If you do not have any atom, there is no one who is actually absorbing this light and moving up the ladder. So, only when you have the number of atoms, then you can talk about those atoms absorbing the photons. So, first of all, this must be a function of the number of atoms that are there in that particular level. Then, because this requires an external energy in the form of photon or in the form of an external energy spectral density, it must also be proportional to the external photon coming in, right. So, the photon flux or equivalently the energy spectral density, which we will call it as a US of omega. US of omega is the energy spectral density per unit volume. N1 is, of course, is the volumetric density. So, this one is the volumetric energy spectral density per unit volume. This one is centered at a frequency omega. Okay. Then he said that it is the product of these two times there is a constant which he called as the constant B, and he put a subscript of B12 to indicate that this transition is going from level 1 to level 2. Okay. So, this is what the absorption should look like, that is what he said. He also said that stimulated emission should similarly be described by another constant B21. It of course depends on how many atoms you have in the level 2, which is N2, and finally what is your photon, the energy spectral density of the radiation that is present. So, this is the stimulated emission. For spontaneous emission, there was no need to have any external photon agency, it happens spontaneously. So, for spontaneous emission, he said that this can be another constant which he called as A21, because the transition is actually from 2 to 1. You have N2, there is no photon energy or energy spectral density of the radiation. Okay. So, these are the 3 processes that are happening in a laser continuously, okay, or in any material which is active. For equilibrium, of course, you want all the process to be balanced out, right. So, under thermal equilibrium, right, the rate of upward transitions must be equal to rate of downward transmission. What are the transitions that are there for upward transition? Only the stimulated absorption. For the downward transitions, you have a spontaneous emission as well as a stimulated emission. So, you combine both and put them left hand and the right hand side. So, you get upward transition as B12 N1 US of omega, that must be equal to the downward transitions, which then becomes the sum of these two, right. So, you have B21 N2 US of omega plus A21 N2, from which we can actually rearrange the equation to obtain the energy spectral density of the radiation, which is US of omega given by A21 N2 divided by, so you can pull this term to the left hand side and then divide by whole thing. So, you get B12 N1 minus B21 N2. This can be rewritten as A21 divided by N2, I am taking it as constant. So, I get B12 N1 by N2 minus 1. Okay. We of course do not know what is A and B relation, and here is where Einstein's master stroke was. He said that this process is actually happening in thermal equilibrium, right, which means that the temperature is essentially constant and it is happening inside a material. Okay. We know the radiation coming off a material or emitted by a material, you know, under equilibrium has to follow Planck's law. Okay. So, Planck couple of years ago had developed the quantum mechanical theory, and he said that if you look at the radiation confined, the black body radiation that is confined in a black body, which is under the thermal equilibrium at a temperature T, this radiation has a particular pattern. Okay. So, you must have probably seen these curves, right. So, as a function of frequency and the radiation intensity, normally you would see the radiation intensity for different temperatures, you would have seen this type of curves, right. So, you would have seen this curve for red, and then you would have seen a blue curve. Blue is at a higher temperature than the red, so it's something like that you would have seen. As the temperature would increase, this is what would have happened. So, you must have seen this, and you must have also seen something like, on one hand you have a Rayleigh-Jeans limit, and then you have another limit. All those things might probably come to you, but we are not concerned with that. What we are concerned with is the way in which this particular radiation pattern looks like, and what Planck had shown was that this radiation can be written as h bar omega cube divided by pi square c cube, and importantly you have 1 by e to the power h bar omega by kT minus 1. Just a note here, h bar is actually Planck's constant h divided by 2 pi. Okay. So, this is h bar, and this should be equal to h bar omega. There is also the refractive index that we need to consider, which is n0 cube. Okay. If it is air, of course n0 will be equal to 1, and you can simply throw it out. So, you have us of omega. The important point is, apart from all these pesky constants like h bar, pi square, c cube, n0 cube, the important thing is in terms of the frequency, it is really omega cube divided by e to the power h bar omega by kT minus 1. You can actually use MATLAB to simply plot this particular curve. Okay. You can plot this particular curve, which is omega cube by e to the power h bar omega kT for different temperatures. So, you try T is equal to 300 K, you try T is equal to 5000 Kelvin, which is very close to the surface temperature of the sun, right. So, you can try all these different temperatures and see for yourself, as you change omega, that you will be able to reproduce these graphs. Okay. So, you will be able to reproduce these graphs. Okay. Now, we have us of omega here, which we have written down. We have a us of omega from this equation. So, obviously, I can relate the two, right. So, I will equate them. So, if I do that, and I do that after, here it should be B12, and I forgot to put B21 here. So, I can take B21 as a common factor. So, I get A21 by B21 divided by N1 by N2 into B12 by B21 minus 1. This would be the radiation pattern in terms of A and B coefficients. This should then be equal to h bar omega cube n0 cube divided by pi square c cube 1 by e power h bar omega by kT minus 1. To proceed further, I do not know A and B, but I do know what is N1 and N2 from thermal equilibrium. Okay. Since N2 is occurring with an energy level E2, or N2 atoms have an energy level E2 which is greater than E1, it is natural, if you do not actually do anything to the system, it is natural, and it is your intuition must tell you that much of the atoms must reside in the lower level, right. The density of the atoms in the higher level, which is at a level N2, must decay exponentially. So, it would decay exponentially, and it does so in this particular fashion. Okay. It does so in this particular fashion, where h bar omega is basically delta E. So, for any energy level difference delta E, it could actually be the air molecules in the beach and the air molecules on the mountain, if the mountain is adjacent to the beach. The number of air molecules on the mountain would be smaller compared to the number of molecules in the on the beach, and the difference is actually the potential energy difference which is required to raise the atoms from beach to the mountain. Okay. That is mg into h, where h is the height of the mountain, and that would be delta E in that particular case. So, anyway, the point here is that if you were to sketch N2 population density, right, as a function of frequency omega, you would see that at higher and higher frequencies the energy basically drops off exponentially. Okay. So, as omega increases, equivalently delta E also increases, correct. So, at higher and higher energy level difference, if you start making, the density becomes less and less, okay, exponentially going down. And this relationship can now be used, okay, to write down the ratio of N1 by N2. So, N1 by N2 will then be equal to e to the power h bar omega by kT. Okay. So, I can substitute that relationship onto the top here in this equation and write here as A21 by B21 divided by e to the power h bar omega by kT. Then you have B12 by B21 minus 1. This must be equal to h bar omega cube N0 cube divided by pi square C cube 1 by e to the power h bar omega by kT minus 1. Now, all you have to do is to pair them term by term. So, when you pair them term by term, you will see that A21, first of all you will see that B12 by B21 is equal to 1, which implies that the upward transition coefficient B12 is equal to the downward transition coefficient B21, and we might as well call this as a constant B. Okay. So, this would be the constant or the coefficient B. The ratio A21 by B21, right, that must be equal to h bar omega cube N0 cube divided by pi square C cube. And there is no reason to keep saying A21, there is only one A here because the transition spontaneous emission is happening from level 2 to level 1. So, you can drop the subscript 21, you can also drop the subscript 21 for B and simply write that A is equal to B times h bar omega cube N0 cube divided by pi square C cube. Is that okay? So, what we have done is to obtain two coefficients. These are called as Einstein's A and B coefficients. Einstein's A coefficient refers to the spontaneous emission, Einstein's B coefficient refers to the stimulated absorption and stimulated emission. Okay. So, this phenomenological theory is quite sufficient to understand how laser actually operates. But let us actually verify this statement that in laser, without an external agency doing something, there is no laser output, right. So, what we mean is that if spontaneous emission is the major contribution to the radiation, then obviously that because spontaneous emission is kind of random, on an average you will not get any net radiation at all. So, it basically kind of tends to average out. Okay. For that to happen, you have to calculate what is the ratio of spontaneous to stimulated emissions. What is the ratio of the spontaneous to stimulated emission? Well, I know that spontaneous emission is proportional to A, right. Stimulated emission is proportional to B into U of omega, the radiation density. Of course, there is an N2 here which has been cancelled out on both sides. So, you can substitute for US of omega and you know from the earlier equation, and then you can substitute for the ratio A by B from the earlier equations that we have obtained and show that this is simply given by e power h bar omega by kT minus 1. Okay. And before we do anything about this one, let us also just at this point solve the spontaneous emission equation to introduce one more variable. So, I know that spontaneous emission dN2 by dt spontaneous is given by minus A N2. I have just put the minus sign from left hand side to the right hand side, and if you solve this, you are going to get N2 of t is equal to N2 of 0 e to the power minus t by tau spontaneous, where tau spontaneous is equal to 1 by A. In the next module, we will look at what happens to the remainder of these equations. Thank you.